Good morning, ladies and gentlemen. My name is Rick Middleton, and I'll be chairing this session. It gives me a great deal of pleasure to introduce Jesse Grizzle. Jesse is a PhD from Austin, and he's also had a postdoctoral fellowship at CNRS in Paris. He's currently Jerry and Carol Levin Professor at University of Michigan. He's done a wide range of things in his research. He's done practical work, particularly with Ford Motor Company, and he has 16 patents relating to emissions control. He's a fellow of the IEEE. He's had a Control System Technology Award jointly with Jeff Cook and a number of other researchers. He's an Axelby Award winner. He's had a Popular Mechanics Innovator Award, amongst a range of other awards. I won't read them all out, but I just thought I'd highlight some of those. Some of these have led to some really high press for some of his work with the robotics. But he's also outstanding fundamental research, particularly in the nonlinear geometric methods area. And as someone who has just a very tiny amount of interest in this, I understood quite clearly, that nonlinear dynamics played a fundamental role in systems. But of course I thought, well, it's a theoretical idea, it's important underpinning, but would this ever apply to anything in practice? How would we use this? Well, wait and find out. Jesse is outstanding in terms of his applications, his fundamental work, and his work is rightly attracting a great deal of attention, both in popular press, and it gives me a great deal of pleasure to introduce Jesse Grizzle as our Bodie Award lecturer. Thank you.
Thank you, everyone. I am extremely proud to be here to share my work on Mabel. Rick, I'm deeply honored that you selected me for this presentation. I've seen the Bodie lectures given from the very beginning, never dreamed of being here, and I have to tell you, it feels good. I want to thank Jay and Elena for organizing it, where it takes place in Paradise, or as we learned last night, next door to Paradise. So I'm here to share with you my excitement and passion for using advanced methods and feedback control to make robots do wild and crazy things. So I'm here because of what my students have accomplished on Mabel. Mabel is roughly human size, but has some special features that we'll highlight shortly. The robot was designed by Jonathan Hurst, but we did all of the assembly, every bolt, every wire, every piece of electronics at Michigan, and it was done primarily by Kaushal Srinath and Haywan Park. Now, their control algorithm development was supported very strongly by prior work of Morris and Poulakakis, and then some technical contributions of Ramazani. And finally, it gives me a lot of pleasure to acknowledge that much of the work we've done on Mabel is based on what we had accomplished with the Robea team in Grenoble, France on Rabbit. Algorithms we implemented in 2004 are still working on that robot. Okay, let's get started a little bit, give you a rough idea of Mabel. So it's 1 meter at the hip, weighs 65 kilos, so it's 155, 160 pounds. The robot is a scientific machine designed for the study of bipedal locomotion. So you want to make hypotheses about how gaits can be organized and then develop the theory and finally test it. Now, the robot is a simplified machine. Its hips only move as 1 degree of freedom revolute joints. They do not move side to side, so it uses a bar to provide stability in the lateral direction. We'll see that the bar does not hold up the robot. It does not have any feet, so it's like walking on stilts. And it has very large springs for energy storage, and it also allows us to create these highly agile gaits. In terms of sensing, it's really the minimal set. There's not a camera on the robot nor in the room. We measure joint angles, and then there are switches on the ends of the legs to detect when we have contact with the ground. Velocities are computed numerically. So let's get an idea of what Mabel can do. So it can walk really slowly. Takes a lot of balance there. For a short time, it held a land speed record for a bipedal robot. Its nominal gait is very robust. Clearly, these are not planned footsteps. It runs with passion. Right there, it's setting a 9-minute mile. And you have to go see it in slow motion to appreciate the elegance of the gait that Kaushal and Haywan implemented on the robot. Now, in all of our videos on YouTube, we terminate them with the robot falling. And the purpose of that is to insist upon the fact that the bar does not hold up the robot. Okay, it provides side-to-side stability, but it's the feedback laws generating good ground reaction forces at the feet that keep the robot upright. Okay, so here's what I want to accomplish in this lecture. Give you some background information on robots and some of the pioneers in the area. Then we'll get into the technical part of the talk on models and feedback control. Some of that will be a little bit tedious. Then we'll do experiments. Those are fun. And then we'll wrap up very quickly. Okay, so why legs and why bipeds? Well, it's estimated that 70% of the land surface of the Earth cannot be accessed with wheels or tracks. And even places where you could go with tracks, you probably wouldn't want a robot using tracks going up and down your stairs. And because of that, there is a surprising number of companies right now positioning themselves for the home service market. Now, we all know what DARPA did for autonomous vehicles several years ago. Well, in 2013 and 14, they're having a DARPA Robot Challenge to try to do the same thing for disaster response robots. Many members of our community are on teams for this event. But, you know, really, what you have to work on is something that makes you passionate and gives you pleasure. And robots are fun. In the lower left, it's Aaron with his robot. It's not just me. All of us have fun. Robots are people magnets. They are better than small puppies. Okay, let's look at some of the pioneers in the area. Some of them human, some of them not. The first walking robot is 40 years ago at Waseda University, WL5. It had a very awkward gait. But through a sequence of innovations, it's been evolved to Wabian 2, a very nice humanoid robot. During those extensions, they came across a control heuristic that they like. They organized the posture of the robot such that the center of mass evolves as an inverted pendulum. So we will come back to these simplified models later. Try to remember, inverted pendulum. Asimo is probably the most famous robot out there. It too is the result of a long line of robot development at Honda. It walks easily up and down stairs, and it can run. Running means you have to have at least a small phase of the gait with both feet off the ground. Go! And there goes Asimo. There goes Asimo in slow motion, and look for the flight phase, both feet off the ground. Hard to see. It's short, several milliseconds. Now, the gait on the robot is as much a factor of the control law used on it as it is the hardware of the robot. It uses something called the zero moment point, where you organize the ground reaction forces on the stance foot in such a way that the center of pressure remains strictly within the convex hull of the foot. This imposes flat-footed walking and flat-footed running, and so you're not allowed to bring the center pressure to the edges of the foot, which cause foot rotation. Now, Raybert's passion was dynamic stability. He said, forget these big fat feet. I will use point feet, and I will design algorithms to keep these robots upright. And they became very, very acrobatic. Now, if you're not familiar with the name Mark Raybert, I assume you know Big Dog and Boston Dynamics. He founded Boston Dynamics. Now, they also built a humanoid, Petman. Look at this bad boy walk. Wouldn't want to meet him in a dark alley. It's quite robust under shoves, handles these massive stairs, and though you can't see it, it's walking across a very narrow plank. Now, they do have cameras in the room there. Raybert's control laws are also organized around a simplified representation of the dynamics. He uses a point mass to represent the center of mass of the robot, and then he assumes the legs are massless and springy. Tad McGear's passion in robots was energy efficiency. He decided he can build a robot that doesn't require sensing, actuation, onboard computing, or any power source whatsoever. In fact, his mechanical assemblages of links can walk down shallow slopes and have exponentially stable periodic orbits. This idea has been taken to its logical conclusion by Andy Ruina. He applied very small actuators at the end of the toes and on the swing legs so that it could walk on flat ground under its own power. This is the most efficient walking robot in the world, bar none. On the other hand, it has one gait, one speed, and could not lift up its feet to clear a book of matches. Okay, so let me try to put these robots in perspective, and you'll kind of see where people are going in the field of bipedal locomotion. So I'll put a notion of agility or mobility, it'll be a qualitative notion on the y-axis, and on the x-axis we'll have energy efficiency. And I'll borrow a measure that's used in the biomechanics community. It's actually a dimensionless number. It consists of energy consumed while the robot is walking, divided by distance traveled, divided by the weight of the robot. So weight is mass times gravity. So this allows you to compare small animals like mice, their energy efficiency in walking, to large animals like elephants. That's why the biomechanist did this. You can also compare machines that are of different size and have a fair comparison. So I will normalize the scales because the numbers are still kind of arbitrary, such that the energy efficiency of a human is 1. And I hope you will accept that Usain Bolt is a highly mobile human. Okay, so let's see our first robot. The Cornell Ranger. It's actually slightly more energy efficient than a human. It uses about 80% of the energy of a correspondingly sized human when walking, but it has one gait, etc., as we saw. Now, what would be an example of a highly agile robot? Well, that would be Big Dog. If you've seen the videos, they are nothing short of stunning. But the flip side is the robot uses 20 to 30 times more energy than a human. That's more energy per unit mass, okay? And unfortunately, Petman and Asimo are more or less in the same ballpark. They are energy hogs. Interestingly, even though Rabbit was not really conceived for energy efficiency, the French robot Rabbit, it uses roughly 6 times the amount of energy as a human. Now, we never got the robot to run, but we came close. Its mobility is not bad. Mabel, you saw, fairly agile, very robust over ground variations. Mabel uses 3 times as much energy as a human when walking. We're building a new robot. Our hope it gets there. You can see what people want now. They really want energy efficiency and mobility in the same package. Working on the extremes, that's pretty much done. You now have to get it in the same package, and it's both mechanics, it takes all of mechanics, electronics, and feedback design to do that right. Okay, so we saw that when the roboticists were designing control laws for these robots, they were using simplified models and heuristics. The problem with heuristics is if I make a small change in the morphology of the robot, or I build a robot that's nearly identical to yours, it takes me just as long to get those heuristics working on my robot as it did you. There's no time savings involved. On the other hand, members of our community work on model-based solutions, which can be transferred easily from one robot to another. And we often make sure that our solutions apply to multiple classes of robots. And then also, in many of our techniques, we include optimization as at least one of the steps so that we can be either the most agile, the most energy efficient, or do a trade-off of those two aspects. Methods employed. Already it's a lot, and it's still growing. There's even more methods presented at the meeting in Maui, and it ranges from passivity, controlled symmetries, to transversal linearization, etc. Many interesting techniques. Okay, so that's by way of background. Let's now get into the technical heart of the talk. We'll start with models. What I want you to understand when we come out of this is the models are hybrid and under-actuated, and hence when we design feedback laws, they're going to have to deal with hybrid under-actuated systems. So let's consider a simple periodic walking gait consisting of alternating phases of single support, meaning one leg is on the ground, and double support, meaning 2 feet are on the ground. In the single support phase, it's a standard open kinematic chain, Lagrangian dynamics apply. Getting the model is very straightforward. Use Newton-Euler, use Lagrange, use whatever you want, and you get the standard second-order robot equations. Now the double support is a little bit different. When the non-support leg, also called the swing leg, comes forward and hits the ground, it decelerates very rapidly. So it's common to use a restitution law type model where you use an algebraic map to calculate or estimate the velocity just after impact as a function of the velocity just before impact. So now you put this continuous and discrete actions together and you have a hybrid model where the switching action takes place when the height of the swing leg above the ground goes to 0. And then you maybe introduce a state consisting of position and velocities, and you have your standard hybrid model, which I've drawn here, assuming we have a single continuous phase. In many applications where you would use this, you'll have multiple phases, but later on, just to keep the picture simple, I will always draw a single phase, but you should understand this theory extends quite well to models with multiple phases. Okay, so that's the hybrid aspect. Let's look at actuation. So the first thing to understand is the concept of degrees of freedom that the mechanical engineers use. So if you look at the position variables and then their corresponding velocities, if there are no constraints on the corresponding velocities, then the number of position variables is equal to the number of degrees of freedom of the model. And then the number of independent torques is the rank of the input matrix B. So a system is said to be fully actuated when there is an independent actuator for each degree of freedom of the robot. And robots that have feet with actuated ankles, they are fully actuated. So it's a common assumption to assume your models have that feature, but I find it to be rather dangerous for the following reason. If you apply just a little bit too much ankle torque one direction or the other, you roll up on the back or front of the foot, and then you are no longer fully actuated. And if your control law cannot deal with the underactuation, you crash. This is even more severe in 3D because standard feet are much narrower than they are long, but this explains why when you see the common humanoids, you have a square foot. They want the same affordance sideways as they do forwards and backwards. So I prefer to look at models, and this is inherited from the work of Rybert. I prefer to look at models with a passive point feet. So the robots are walking on stilts. They're definitely under-actuated. And what's nice about that is if I get the robot walking with point feet, as you saw earlier, and now I add a prosthetic foot that's still passive, I can use exactly the same control law. And there, I don't know, who's walking better, Mabel or the cameraman? You choose. Another way that under-actuation comes about is if you have a series elastic actuators. So this means an actuator or spring, and then the end of the spring is connected to a joint. The spring is used for storing energy or for filtering high ripples on torque, etc. Okay, so our models are hybrid and under-actuated. Let's see how we can design feedback controllers for these models. So I want to give you some control intuition, some control theory, and some control computation. Now my real motive is to have you at the end understand the relationship between hybrid invariant surfaces in hybrid models and gates in bipedal machines. You can tell me how I do at the end. But remember, we're going to start with the intuition. The intuition is that you can use holonomic constraints on a machine to synchronize its joints. I will draw my example from Theo Janssen, who is a world-renowned kinetic sculptor. And I want to add that Theo Janssen was not inspired by my work, but my methods did not come from him either. But it's just a fun way to understand the notion I want you to get to, which is a virtual constraint. So here we go. That's Theo Janssen. Here's a cartoon of one of his machines, all the links coordinated via a crank.
He manages to make things that look so close to being alive that you almost can't believe that they aren't.
I know you'd like to see more of that, but we don't have time. So there's dozens and dozens of legs on there, hundreds of links, all synchronized to a 1 degree of freedom device called a crank. Okay? So this is what I mean by using joints being synchronized to a crank. Now these are imposing a set of holonomic constraints, so they are done physically with bars, chains, gears, etc. I will call a constraint virtual if I do not use the gears and links to impose the constraints, but I use feedback to do that. So what do I mean by that? Okay, so here's Theo Janssen's mechanism with the links connected to the crank, imposing his set of physical constraints. I remove those connections. I equipped his device with sensors and actuators. I probably need to add an embedded processor as well. But then I pose a control problem. I define an output that's equal to the positions of my joints minus how I want them to evolve if they were actually connected to that crank. And then I design a feedback controller that drives those outputs to 0. And if I can asymptotically get them to 0, then I have imposed these constraints in a virtual manner. That's what I mean by a virtual constraint. Okay, easy said, because Theo Janssen's mechanism has a crank. Where is the crank on a biped? Oh, look at the line connecting the hip to the toe, and look how it evolves during a step. This gives me a hybrid virtual crank that resets after each step. It's monotonically increasing. So what I can do on the biped is synchronize the evolution of the knees and hips of my robot's joints, for example, to this virtual crank so as to synthesize a gait. And if you have a hard time imagining this, here's it being done on a robot. The students are pushing this bar forwards and backwards, which makes the crank angle, the virtual crank angle, advance and go back. And the joints of the legs are simply being commanded to play out a gait. Okay, so it's just walking forwards and backwards there, being pushed passively, but the motion is ensured by virtual constraint. Okay, so that's the intuition. Replacing physical constraints with feedback, sensing, and actuation to get a virtual constraint. The advantage of a virtual constraint, I can change it by changing a few lines of code, where Theo Janssen has to get out a hacksaw and glue to modify his mechanism. Okay, so this is the technical part of the talk. Hold on, here we go. First thing to understand, what does a periodic solution of a hybrid model look like? Our system is hybrid, so it has a switching surface. It's a hypersurface, meaning it's codimension 1 in the state space of my continuous model. Solutions are defined by following an initial condition of the continuous dynamics until I impact the surface. Then I apply the reset map. Then I continue with the flow of my continuous portion of the model, et cetera, et cetera. I think you get the idea. That's what a solution means of a hybrid system. Now, what is a periodic gate? Well, if after I apply the reset map, I come back exactly where I started, I now have a periodic motion. So this would correspond to a periodic walking or running gait in a hybrid, in a hybrid model of a robot. Okay, so let's now move on to understanding, well, how do virtual constraints play out in this mathematical environment? So I add my differential equations from the continuous phase of the model, and I pose my outputs, which depend only on the position variables, so they are virtual holonomic constraints. What I want to do is design a feedback that drives y to 0. Unfortunately, this is mathematics, means we actually have to make hypotheses that are correct under which we can actually do this. So what I'm going to do is assume some regularity conditions, a little stronger than I actually need just to keep the discussion simple, but I will assume the outputs have vector relative degree 2. So what does that mean? So if I differentiate my outputs once, they will depend upon the velocities. I differentiate the derivative of the output, it then depends upon the accelerations. My second order model, the accelerations are related linearly to the torques in the model, hence the second derivative of my output can be written down as a matrix times the torques in the model plus a lot of other messy stuff. If this matrix I've underlined is square and full rank, then the outputs and the system has vector relative degree 2. Okay. So under this, we can do two things. We can for sure design a feedback that sends the outputs to 0, but according to Burns and Isidori, we can do much more. In particular, we create a surface that's given by the set of zeros of my output and its derivative. And this feedback that I apply to create this surface has the property that the closed loop system renders this surface invariant, meaning if I start with initial conditions on the surface and I flow along the solutions, I stay on that surface. And so this is definitely the Burns-Isidori zero dynamics of 1988. In the case of these robot models, you can write it down in a form that looks like a second-order system, and sometimes they are Lagrangian and sometimes not, because our actuators do inject power. Okay, now we did all that design of the surface without taking into account the reset map. So when we apply the reset map, we may end up on the surface or we may not. Well, we've studied the problem of how you can automatically come back to the surface. We've studied it a lot. We know a number of situations. We know exactly how to design that surface such that it's invariant under both the continuous and discrete portions of the model. And very importantly, we know how to design that surface so it does not limit the kind of periodic orbit I can create. If I can create this invariance, but I only get orbits that use a lot of energy for walking, it's not interesting. If I can design this invariant surface and I only get gates that are stumbling and not very fast and agile, it's not very interesting. So you want to prove that there are essentially no restrictions on the type of periodic orbits you can achieve when you also deform the surface to make it invariant under both the continuous and discrete aspects of your model, and this gives you the hybrid zero dynamics. Okay, so we're pretty much done with the hard math. What we have now is a divide and conquer approach to designing gates for bipedal robots. We separate the problem into proposing a set of virtual constraints, creating an invariant surface, and that's shown on the left, and you get a nice low dimensional model, and that is essentially separate from the feedback that you use to drive the set of virtual constraints to 0 that actually imposes that surface and makes it invariant. So what do these hybrid zero dynamics tend to look like? So Mabel The model has 12 states or 14, depending on how you want to look at it, but the springs on the robot are so stiff that when a leg is off the ground, the spring is essentially not there. So in that case, we get a 12-state model for the robot. The zero dynamics look approximately like the spring-loaded inverted pendulum of Raybert, with the difference that it's a distributed mass pendulum, and there is some damping in parallel with the spring. If you go back to the French robot, which has no springs, it has a 10-state full model. The hybrid zero dynamics has 1 degree of freedom, 2 states, and it is a distributed mass inverted pendulum. Let's look at how you design outputs to drive these virtual constraints to zero. Well, one way to do it is to apply the classic robotics method of computed torque. We call it input-output linearization here at the CDC. That works okay. A way that we've just started investigating is called control Lyapunov functions. We're using the work of Artstein and Eduardo Sontag. So to do this, you define a positive definite function on the output and its derivatives, only y dot here because I'm doing relative degree 2. And then you want to differentiate that function and choose the input such that v dot is sufficiently negative definite. Here we would have local exponential stability. Okay, so key is rendering v dot sufficiently negative definite. Now what's interesting is you can try to choose the control u of smallest magnitude that meets that inequality. Randy Freeman taught us how to do that. So you can set up a problem, choose u of minimum norm, such that v dot is sufficiently negative definite. Even more, you can add constraints to it, so you can explicitly account for constraints in your feedback design. We did not know how to do that with input-output linearization. This gives rise to a quadratic programming problem that we can solve in real time on an old embedded processor on Mabel in 2 microseconds using some code of Stephen Boyd. So Aaron Ames and Kevin Galloway will present that result this afternoon, and I will save the video, it's really interesting, for their talk, so please go see the talk. Okay, we have once again this divide and conquer. The final thing we need to do is just to make sure that, we've done the divide, we've done the conquer, we've got a periodic orbit in the hybrid zero dynamics, our y's are being driven to 0. Does that make everything work in the whole model? Do we actually get an asymptotically stable or exponentially stable periodic orbit in the overall model? So I have no time to explain Poincare maps, just to say, everybody who knows Poincare maps, that's what you do here to check stability. The hybrid invariance part allows you to carry out your analysis only on the hybrid zero dynamics as long as you make the dynamics and the y variables converge sufficiently rapidly. That's what the theorem says. Now, your solution in the hybrid zero dynamics is often already asymptotically stable, but we know cases when it's not. And there what we do is we introduce a few extra parameters in the orbit, and we render the Poincare map into a discrete time system evolving on the Poincare surface. We then design feedbacks to stabilize that equilibrium point, and so we have a truly hybrid controller, continuous action and discrete actions. And with that, I will close with the theory on feedbacks. Okay? Okay, let's now look at feedback computation. So we try to make things easier for ourselves by posing these virtual constraints in a very special form. We pose them in the form of things we want to control and their desired evolution. Choosing what to control is an art. It varies heavily from one robot to another. We have learned how to make these choices by studying analytically special classes of models that have features that are similar to the real robots that we have in our lab. We've done that in 2D and 3D. We've done it for robots with springs, without springs, etc. And I'll show you what we actually control on Mabel once we understand better the actual hardware of the robot. So let's go to the part that's pretty much systematic. That's designing the desired evolution of these virtual constraints. Notice that we parameterize them in terms of this virtual crank. So it's a phase or timing variable for us, but it's not time. It's monotonically increasing. We choose these functions amongst a family of splines. We give ourselves a number of free parameters to choose. Those parameters are chosen by optimization. Another beautiful feature of the work of Burns and Isidori is I can have a whole family of output functions, and I can still calculate in closed form the torque I need to go on that to slide along, to move along the family of invariant surfaces created by their theory. That allows me then to pose a cost function. Here I'm using roughly the integral of the energy in the inputs divided by the length. If my mass of the robot were varying, I'd throw that in, then it's really cost of transport. So I minimize that cost function where I'm integrating the dynamics over the reduced order model. So for Mabel, this is a 4-dimensional state space instead of a 12-dimensional state space that I have to integrate in order to solve this numerical optimization problem. And it's here that I impose constraints that give me the various features I want in my gait, whether it's periodic or not, a desired walking speed, how the ground reaction forces have to be to keep the robot upright, etc. Now my students know this, and anybody who's going to use it needs to know that this optimization problem is really the hardest part of the whole theory. It's non-convex, many local minima. We use multi-start, etc. But it would be nice to have better methods here. Okay, so that's the overall feedback design process. Let's go ahead and apply this to Mabel. So Mabel's hardware, we've already seen she has these very large springs. They're not so elegantly packaged, but she was designed by a PhD student at Carnegie Mellon, so it's a pretty interesting robot. All of the motors, the gearing, the power electronics, etc., they're all up in the torso of the robot. So this makes the body have a center of mass that's roughly human-like, and the legs are relatively light, and you want light legs if you're going to run them back and forth. The gearing and motors are organized into a set of differentials. The outputs of these differentials are connected to the hips and the knees. Now, it's a little easier to see if I turn these differentials sideways. The bottom two differentials are forming linear combinations of torques from the motors to spring, from the two motors and the springs. Those combinations are organized as follows. Let's look at the very top of the differential. That forms a series connection of a motor and spring, and the bottom differentials organize it such that that torque is applied on the line, the virtual line that connects the hips and the ends of the feet. That turns the leg into a pogo stick, as you saw when Mabel was running. And then the other motor controls the angle of that pogo stick with respect to the body. Now, if you understand this qualitative view of how the robot goes together, then what you want to choose as the H0 portion of your virtual constraints becomes more intuitive or obvious. Because the torso is so heavy, keeping it upright is very important. So one of the things we control is the absolute angle of the torso. Now, how do you get energy in and out of the legs? Well, you need to move the rest point of the spring, and so we do that. And then on the non-stance leg, once again, the spring is so stiff there that you can treat the leg as if it is non-compliant, and so you can just control the angle of the knee and the hip such that it folds properly and then brings itself forward and prepares for the next impact. So that's the choice of virtual constraints. And when you do that, that's what gives Mabel this distributed spring-like inverted pendulum characteristic. And now with that in mind, look at Mabel running here in slow motion and see the nice bounding gait that she has. And you don't need a high-speed camera to see that the legs are high above the ground, and in fact 40% of the gait is spent in the air. Okay, let's go back to walking. Let's just do a basic walking controller using the methods that I've outlined here. So we're going to assume the environment is flat, and if by chance gentle ramps and steps up and steps down get introduced in the lab, we'll try to handle that by fundamental robustness of the controller. Remember, the Mabel has no sight, it's blind. So we'll use the cost function I mentioned before. We'll shoot for a periodic gait. We fix the speed. We'll make sure that we don't need a super large coefficient of friction in order to keep it upright. And the only thing I'm going to do here that I wouldn't do for absolute best efficiency is I'm going to make sure the swing leg has 3 centimeters of clearance in the middle, so it has the possibility of stepping up onto an obstacle. Okay, so here's our basic walking gait. Da-da-da, da-da-da. Walking around the lab. I don't have eyes. I'm completely oblivious to what's coming up. I don't care. I just walk all over it. Okay? That's Mabel. At least that's how we think Mabel thinks. Okay, so they're just going to keep adding obstacles until the robot falls. It slowed down there because it had to turn kinetic energy into potential energy. Even more higher step, more potential energy. Okay, so I've sped things up in between, obviously, so the video doesn't take forever. Now watch this one carefully, please. Pretty neat emergent behavior. If you're using virtual constraints, you don't care if the robot's hip moves with respect to the ground or the stance leg moves with respect to the hip. You get the same forward motion of the swing leg catching the robot. It's amazing. Now watch this next lap carefully. Ouch! That was Mabel's delayed pain call. Actually, it takes us about 20 minutes to put the leg back together. It is a mechanical fuse held together by nylon pins. It's designed to be there. But what you see is that, okay, the basic walking controller is quite robust, but it cannot handle arbitrary large perturbations. So, our next phase was to move into putting in some fairly large perturbations. And in each state of the process, I'll try to give you a little bit of idea of the state of the art, the challenges, and then underline also that the obstacles are unseen. So if you're doing unknown ground, there's 2 cases you have to consider. One, where the robot has a camera, or you have a Vicon system in the lab that's giving the ground profile to the robot. In this case, robots like Asimo, etc., walk up and down stairs with no problem whatsoever, okay? Raybert had robots jumping over very large blocks. This takes careful planning of foot placement, etc. So we don't have a camera, so we don't work on this. On unknown ground, you assume there's no camera information being used either on the robot or in the lab. And there, the state of the art in terms of ground perturbations is roughly 6% of leg length. Now I give it as percent of leg length so it doesn't matter whether the robot is short or tall, it's the same relative size obstacles, okay? Now Mabel's legs are 1 meter long, so 6% of leg length is 6 centimeters. Okay, so, and what we were doing with that, with the baseline controller when the leg broke, strangely enough, that was about 6 centimeters when it broke, okay? Really is state of the art. So I challenge the students to think big, really big. Can we step off something that's the height of a standard step in a stair, 20 centimeters? Okay, robots are more capable than us in one aspect. So when Mabel is in a position like this, because it knows the positions of its joints, it can measure in a millisecond the depth of the height difference between the two legs, okay? So once it has stepped off an obstacle, it knows what it's dealing with, but before that, it has no idea, okay? So keep that in the back of your mind. Now, when you step off, you have a huge reduction in the amount of potential energy, so all of that is converted into kinetic energy. The torso's bouncing everywhere, and you have broken legs. So what we decided to do, well, the student decided to do, he didn't consult me, was to turn the leg into a huge shock absorber after that step. The parameters in the shock absorber were designed using optimization, very similarly as we've discussed before. And what he was really working on was the ground reaction forces and making sure they don't get so big as to cause the leg to buckle. And he understood that the torso pitching was a secondary cause of the leg breaking. So he minimized the amount of torso pitching subject to bounds on ground reaction forces so it wouldn't slip, etc. Now, a priori, we already knew the baseline controller could handle a 5 centimeters step down. So maybe we need to design several of these, one that works between 5 and 10, another one between 10 and 15, one between 15 and 20, etc. And then once the robot has stepped down, we know how good it is, we just switch into it and go, right? Turns out the baseline controller and one other is enough to cover the entire range. Okay, so the controller that handles 20 centimeters will all go all the way down to 5 and work just perfectly. So we can use a single additional controller in tandem with the baseline controller. So here's the controller in action. Boom, like nothing, okay? I wish I could do that. Slow motion, we measured how much the ground depth is, we apply the correct controller, we wash out the energy in the system with the shock absorber, we transition back to the next phase, and go on like nothing happened. I'd be picking myself up off the floor. Okay, so that's one thing to be walking and step into a hole. We've all done that. We're walking and we're talking to someone, and we step off the curb, and it hurts, okay? But often we manage to stay upright. The things that really get us, though, is when we're walking and we trip over something. That's really, really unpleasant. So remember, Mabel has no camera, so I didn't really think it was possible that we could deal with tripping things, at least nothing very large. It's always good to have students who dream bigger than you do, okay? So we're working now on extreme stability for disaster situations. What I'm showing you is the helmet cam of a firefighter. So if you had a vision system, how good are you going to be at estimating the ground height there? Might as well keep that blindfold on, okay? So what we did was to give Mabel a chance to detect that obstacles were there. We put an additional switch on the front of the shin. It works like the nerves in your toe. You bump into something, you get feedback information. So now the robot has feedback information from the base of the foot and the front of the foot. And using that information, they want to design controllers that allow it to handle tripping obstacles. Okay, so then when you hit, a couple of things can happen. I'll just show a few of them. Keep this short. You could step up on the obstacle if it's wide, but if it's narrow, then you'll step over it. And you have no idea when you first start which one it is going to be. You just have to act differently once the leg has either landed up on the obstacle or back on the floor. So then we used a finite state machine to stitch all of these controllers together, and here's some results of it. Want to try this one at home? Remember, no camera, but it looks like it has eyes in its feet, okay? No camera. There's the state machine, step up, regular walking, step down, back to regular walking. Now we'll go back through that obstacle with a different initial condition. Up, regular walking, all the way down in one step, okay? Good thing that step-down controller works. That would hurt. Okay, at this point, we feel like we are geniuses, okay? But here's the dark side. Aha. There exist executions of my finite state machine which result in failure. Okay? Things I cannot handle. Here's one of them that you just saw. So what's particularly hard to handle at the moment is to go directly from a step down to a step up without a regular walking step in between. The regular walking controller is so robust it just washes out all the perturbations in the robot and it's ready for the next perturbation. So if I could just arrange that all my obstacles that the robot would see were like that, we're done, but I can't, right? So now here's my problem. I don't know if I need to add more behaviors to my finite state machines, such as a step down, two step up transition without a step of regular walking. Or I simply need to design a more robust step up controller that can handle a wider range of initial conditions that could be coming out of the regular walking and the step down. I don't know. How do I find out? This is a very interesting analysis problem, and we're stuck here at the moment. Okay, so let's wrap up. Hope you've enjoyed this. It's been my pleasure to be with you here this morning and give this Bodhi lecture. So the state of the art in control locomotion, if you're walking over a known periodic surface, and your robot is planar, the theory is in pretty good shape now. I mean, it's not perfect, there's still things to do, but a lot of the big ideas are there. There's quite a few experiments demonstrating that the controllers designed in theory seem to work in practice. There's some theory in 3D, very few experiments, so we need definitely many more experiments on periodic surfaces in 3D, especially for highly dynamic gates, and much more theory. When it gets to aperiodic surfaces, we're still pretty much in the dark. Russ Tedrick's group presented a very nice result on Monday. My group has a few results, but I promise you there's lots to be done, and I invite you to join us in the adventure of finding these solutions to these problems. We have retired Mabel. She'll be on display eventually. She's lying in a box on the floor at the moment, kind of sad. But we've got a new robot named Marlowe. Marlowe is 3D, doesn't need a boom for side-to-side stability. Its hips are complicated enough that they can move forwards, backwards, and sideways. It has onboard power, onboard computation, etc. And what my team is working on now is to try to get Marlowe walking well on flat ground, and then we're going to start looking at these highly agile, extreme stability motions with good energy efficiency. And with that, I thank you.
So thanks, Jesse. I think that's a fantastic illustration of what can be done with a good practical design and control theory, revolutionizing really the whole way you think about the problem. So thank you once again, and Jesse will be happy to talk to you after the talk if you have further questions or comments. So thanks once again, Jesse. Fantastic.